All right, so I want to have a look here at a few of the problems on the worksheet. I'm going to start with this one here because the wording of it often... Oh, you need that. I don't need that. Yeah, no, you keep it. It's your receipt. Okay, so I want to look at this one here in particular because people get thrown on this one because of the way we've been talking about how centripetal force works. Okay, we've been saying that whenever you do a centripetal force problem, you have to identify what force is acting as a centripetal force. Okay, and then you have to set centripetal force equal to that. And people just start doing that on this question when they actually don't have to. Okay, I mean, in this question, what is acting as a centripetal force? Gravity is acting as a centripetal force. But you have to also look at what I'm given here. Okay, I mean, I could certainly say that FC equals FG. Okay. That's true, and it's one of the things we're going to do later on in the unit. But this particular question tells me the mass of the satellite, times 10 to the 3 kilograms. Okay, it tells me that it's at a distance of 1.8 times 10 to the 7 meters from the Earth's center, which would be the radius. Okay, that's the orbital radius. It's always measured from the Earth's center, not from the Earth's surface. Okay, and it's moving at a speed of 4.7 times 10 to the 3 meters per second. All right, so if I'm looking at this formula here, I got mv squared over r. Do I already have all of those things? Yeah, so I don't need to worry about what mv squared over r equals in terms of a formula. Incidentally, it's this. But I don't need to do that yet. We will, like 2 weeks from now, okay? Because I already have all the information necessary to calculate what they wanted, the force acting on the satellite. I can calculate that just using mv squared over r, okay? So always make sure, the lesson on this question is always make sure you look at what you're given, okay? Do I need to go and get really complex, or do I have all the stuff I already need? Okay? In this question, it's just a matter of plugging numbers in. So we go 2.7 times 10 to the 3 kilograms, okay, times 4.7 times 10 to the 3 squared, okay, divided by 1.8 times 10 to the 7 meters. All right, so when we do that, okay, we're going to get 3.3 times 10 to the 3 newtons. Okay, that would be the gravitational force acting on that satellite. All right, question? How come it's not the same as gravity? That's a good question. All right, so the question is, how come this doesn't come out to the weight of the satellite? Okay, the answer to that question is it doesn't come out to the weight of the satellite because the satellite's not sitting, it's orbiting. It's further away. The further away from the Earth I get, the less the pull of gravity becomes because of the formula I had up here a second ago. Okay, this formula here, okay, big G times the mass of the Earth times the mass of the satellite over r squared. Okay, that is the formula for the force of gravity that I would use if I didn't know what little g was. Okay, because little g is only 9.81 if I'm standing right here. Okay, as soon as I start moving away from the surface of the Earth, or sorry, from the center of the Earth, then gravity becomes less and less and less. And it becomes that way exponentially. Okay? The further away from the Earth I get, I will be exponentially less attracted to it, gravitationally speaking. All right? Everybody follow me there? Okay? So that's why it doesn't come out to that number. Okay? It's a good observation. Okay? It doesn't come out to that number because the further away we get, the less gravitational attraction there will be. Okay? Everybody all right with that? Okay, I want you guys to keep working on these ones here because I think there's a few that are going to possibly give us some trouble as we go along, and we're going to get into away from the unbanked curves. Okay, like the first bunch there was quite a few unbanked curves, but they will be getting into some bank curves. Okay, and we only did a couple examples of that yesterday, so we'll get into those and see how we do with those. All right. Okay, so give those ones a try. I don't think that'll take us all class. We'll be getting into some stuff on artificial gravity, I think, here before the end of class. Okay, you know how music used to come on big black Records. Okay, that's what this is about. It's starting to come that way again because apparently, like, DJs really like to use the records, the old style vinyl records. Okay, so there were two types of records. There were small ones called 45s because they would spin at 45 revolutions per second, and then there were or per minute, sorry, and then there were the big ones. Okay, the really big ones spun at 33 1/3 revolutions per minute. Okay, so when I'm giving you this 33 1/3 revolutions per minute, it means it goes around and around 33.3 repeating times in 1 minute. So I've given you a frequency or period? Frequency. All right, so that's what that's referring to. It's not 33 to the power of 1/3, it's 33 1/3. Okay. Okay, in terms of wording, if it says, like in question 11 here, what's the maximum speed of a car rounding a 125-meter curve? That's the radius. Okay, curves are always described in terms of their radius or by reference to their radius. So if it says a 125-meter curve, it's a curve with a radius of 125. Okay, it's not the circumference. All right, so with number 13 here, we've got an airplane traveling. We know the speed it's traveling at is 115 meters per second. It makes a complete horizontal turn, so a complete circle, okay, in 1.2 times 10 to the 2 seconds. So that's period. 120 seconds. Okay, what's the banking angle? So we're looking for theta. All right, I know V and I know period. So what can I find with those two numbers? They're in a formula together, right? They're in this formula together. What can I find? Radius, and I need that if I'm going to use the bank curve formula, because that's what this is. It is a bank curve. That's going to be V squared over R times G. So I need R for that. All right, so I'm going to calculate what R is. R will be V times T divided by 2 pi. All right, that's how I'll calculate that. So for this one, that will be 115 times 120 divided by 2 pi. Okay, so we're looking at a radius here of 2,196 point something meters. Okay, now that I know that, now I can use my bank curve formula to find the banking angle. So to find the banking angle, I'm going to go tan to the -1 of V squared over R times G. Okay. So that'll be 115 squared divided by our 2,196. Okay, times 9.81. All right, so we're looking at the the tan of the banking angle is 0.613. So if I go inverse tan of that number, okay, I get 31.5 degrees. Yeah. So tricky two-step question that we had to find one thing before we could use this formula here. Okay, any other ones giving us trouble? Okay, keep her going then. Okay, so obviously there's some applications on Earth of uniform circular motion, and one of those would be in amusement park rides. We talked about the Gravitron just briefly the other day. Okay, that ride at the Calgary Stampede that spins around really, really fast, and then eventually the floor falls out and you don't fall because you're pinned to the wall. Okay, well, the same idea, and the reason that ride is called the Gravitron is because it's essentially generating artificial gravity. All right, we want to be able to use that, because one of the main health concerns for astronauts in space is the effects of zero gravity on the human body. The human body evolved in a gravity environment. Thus, a lot of the things that work in our body actually depend on gravity, especially things like balance. Okay, on Earth, okay, we know which way is up and down, and we keep our balance because of what part of our body? Well, it's something attached to the brain, which I guess doesn't really narrow it down because everything is, yeah, your ears. Okay, in the middle ear, okay, the inner ear, there's the the semicircular canals and all of that kind of stuff, and in there is your balance center. Okay, and in there essentially is like little, it's not grains of sand, but it's like grains of sand, okay? And little hair cells. They're not hairs, but they're like that, okay? That's what they look like under a microscope. So when I tilt my head, okay, these little like grains of sand roll to one side and they stimulate the hair cells to tell my brain, we're starting to lean. So you should probably tense the muscles on the other side of the body so we don't fall over and look silly. Okay, it's just the stuff that your body does automatically without you thinking of it. It's the thing that tells you if you're crooked. Okay, it's the thing that tells you if something's not level. Right, all of that stuff is important for you to not fall down. Okay, in space, that system doesn't work at all. Okay, because those little grains of sand are going everywhere. Okay, and they are constantly screaming at your brain. Okay, they're like that car alarm that just goes off all the time. Okay, there's nothing wrong, but it's always going off. What eventually do? We ignore it. Stupid. Nobody's breaking into that car. Of course, at that time is the opportune time to break into that car because nobody's taking it seriously. It's the boy who cried wolf kind of thing. Okay, but okay, when it's your brain, when it's the balance center telling the brain, okay, and the brain starts to ignore it, then how does the brain tell which way is up and down? What's the next best thing to tell it which way is up and down other than your balance center in your ear? Your eyes. Okay. Relying on your eyes for balance cues changes your perception of things drastically. Okay. And it works in a zero gravity environment because your brain's pretty flexible. Okay. And it's tired of hearing the middle ear yelling at it. You're upside down, you're sideways, you're straight up, no, you're sideways, oh crap, I don't know, we're gonna throw up. Okay, and that's often what happens to people over the first few days, okay, is because the balance center is just constantly sending the brain these bogus messages, they just get physically ill, all right? And that can be dangerous, okay? If you're in a spacesuit and you puke, you could die, because what'll happen? Yeah, you'll aspirate your puke. Remember, you're in space, there's no gravity, puke doesn't fall. That's another problem with zero gravity. Nothing falls in zero gravity. Okay, so if you throw up, it just goes everywhere, and you could inhale it, and that's really, really bad for your lungs. Okay, because that's really acidic. Your lungs are very delicate; they're not supposed to have puke inside them. Okay, so you want to kind of generally keep stuff like that out of there. All right, so the human body is an intricate system that depends on gravity for lots of things. Okay, we've only talked really about balance. Okay, but the balance part's important. If we send a crew from Earth to Mars, they're going to be in space for at least 6 months. If there's no artificial gravity, they'll be in zero gravity for 6 months. A number of things will happen. First off, over the first few days, their balance cues will change, and they'll start relying on their eyes, which is fine in zero gravity. But when they get to Mars, gravity returns. It's not as big as it is on Earth, but it's there. Okay. But their brain is used to listening to their eyes for balance cues. But once you return to gravity, you start using your eyes to scan the horizon and do things. Your brain's used to that telling it about your orientation. Okay? This is why when astronauts come back from the International Space Station, you don't see them for the first little while. Okay? When they used to come back off the space shuttle, they had this ramp with these big handrails, and they would come down off the ramp and they'd like wave, and then they'd look down at their feet and walk down. Okay, they never kind of looked around and walked down because if they did, they fall over the side. Okay, when they first get back, someone greets them at the bottom, and there's one person with either arm. It's not because they're weak or because they're, there's something wrong with them. Well, there is a little bit something wrong with them. Okay, it's that if they turn to the side, they'll fall down, because their brain is used to their eyes telling them which way is up and down. So as soon as you do this, and your brain's used to that being a balance cue, it's like, we're falling! And your muscles clench on the other side, and you fall. Okay? Because it's telling it the wrong messages. All right? They actually look, okay, because they actually look drunk. Okay? And Chris Hadfield was saying, like, you can't pass a field sobriety test when you come back for the first few days, because you can't walk in a straight line unless you really concentrate and only look at the line. Of course, part of a field sobriety test is you're not allowed to look at the line, right? They're saying, look at me, and walk this straight line, okay? Because the same thing happens to your brain when it's intoxicated. The balance center starts to revert away from the middle ear, okay? And you start doing weird things. So the same thing happens, and these guys, if they're walking along and somebody says, hey, Chris, what? And just like they turn and fall. Okay, it's really, really weird. So that's part of it. But the other part of it is the things your body does automatically, okay, like recycling. If you're not using your muscles as much, what's your body going to do to them? It's going to break them down. Okay, your body's the ultimate recycler. If something's not getting used, it'll break it down. Muscles, bones. Okay, if there's no weight bearing going on, your bones will get weak. Okay, and this happens to astronauts. They have to be very, very mindful of these things when they're in outer space. But they can't just go, oh, my bones are going to get weak, I'll take calcium supplements. Because if they do that, they'll get kidney stones. Because their body's already breaking down the calcium in their bones. They take more, they just add more, and eventually it starts to form little, really jaggedly sharp rocks in your kidney. Okay, and that really hurts if you try to pee them out. Really hurts. Okay, so we don't want that. It's also it's not a healthy thing because they're jagged little rocks and they can cut your urinary tract on their way out, and that can cause an infection, which can be very dangerous if you're not, let's say, within 1,000,000 kilometers of a hospital. Right? It's not like they have, a whole bunch of antibiotics and things like that on the spacecraft. Obviously, they would have some, but an infection is a pretty serious threat to your health if you're not near like appropriate medical care. So these are all things that they have to be concerned with. The muscular atrophy is a really big problem. Okay, this happened. They found this out the hard way with some Soviet cosmonauts. When the Soviet Union crumbled, they had a crew on their space station at that time, and they had no way to get them back. Okay? Their space program was broke. They couldn't send anybody. They couldn't send a Soyuz capsule up to get them. They wouldn't let anybody else go up there. Okay? The Americans were like, hey, we'd be glad to go up there and get your guys and take a look at all your stuff. Okay? And of course, the Russians were like, niet. Okay? You're not going. Okay? To Mir. So these guys ended up being up there for a very long time. All they allowed them to do was send up unmanned modules with food and water. Okay? So that they would survive. By the time they got back, they had been in zero gravity for so long that the muscles for breathing had atrophied to the point where when they got back onto Earth, they had trouble breathing. Okay, we don't even think about that, but it requires working against gravity. Okay, to ventilate your chest has to expand, increase its volume, the lungs will expand and air rushes in. Okay, those intercostal muscles and your diaphragm, if they atrophy and then you return to a gravity environment, they're not strong enough to lift your rib cage. And you can suffocate. Okay? These guys had to be put on supplemental oxygen for a matter of weeks until their respiratory system was strong enough again in a gravity environment for them to do that. Okay? Not to mention the fact that they had bones like a 75-year-old. Right? They had just gotten, essentially you get osteoporosis if you're up there for too long because your bones are not being used to bear weight anymore. Okay? When you get older and you start to, and I'm not saying like my age, like even older than me, so, less, just over 100. Okay? You'll start to get something called osteoporosis. Your bones break down, they become porous and weak. Okay, and what they tell people to do when they start getting that is you need to exercise more. You need to and I'm not saying like get in the gym, man, pump iron. Okay, I'm just saying like they got to get out and walk. Okay, because when they're walking, there's that impact. That impact creates microfractures in the bones, which then heal and make the bones stronger. All right, in space, you don't get that. There's no weight. Okay? So what they have to do is they have to use essentially a Bowflex. Okay? They have a Bowflex there that helps them use their muscles because putting plates on a bar in space doesn't do very much. Okay? You don't do bench press in space. You'd look really cool for about a half a second, right? Put 500 pounds on there and go like this. Okay? But once you get to here, what's going to happen? Yeah, off you go, okay? Because now there's no gravity and you got that thing moving and Newton's third law is going to be in full effect for you, okay? So yeah, they don't do that. Plus, it's expensive to move weight into orbit. So we don't want to have to do that. So a Bowflex is a lot lighter. It's not like a Bowflex, but essentially like that, okay? They also have a special treadmill. Okay, a special treadmill that they can run and walk on to help with their cardiovascular condition, as well as give them that bone impact. So it's got this thing that looks like a life preserver, okay, that goes around their waist, and a vest as well that's attached by bungee cords to the treadmill. So that when they run, okay, they can't fly off of the treadmill, okay, but it creates an impact against their bones, okay, that helps to keep their bones healthier. Even with all of that, okay, and this is what Chris Hadfield's research was all about. When he got back, they did bone density scans on him, and he had the bone density of a 75-year-old when he got back. Okay? And that was even with doing all of that stuff, and he was only on the space station for, I think, 6 months. Okay? So there's some serious health concerns with sending people to or on a long space journey with no gravity. Okay? Some pretty major health concerns with that. Okay? The other thing that happens is that fluid redistributes through your body in zero gravity. Okay, normally with real gravity, okay, the fluid doesn't collect in our extremities or our face unless it's our feet, because gravity pulls it down to there. Okay, over the first few days when astronauts are in space, the fluid redistributes over their whole body. And actually, sometimes if you see the pictures of these guys, they look like they've just gone like 10 rounds of bare knuckle boxing. They're swollen across their face. Okay? They sound congested because all of this fluid that normally collects, in your feet or wherever is now distributed equally. They feel arthritic because their hands and their joints are all full of fluid like they normally wouldn't be. Okay? And they feel that kind of swollen, stiff, sore feeling. Okay? As a result, okay? That can be a problem as well. All right, so the way to get around that is to create a spinning drum. Okay, make a space station, or at least part of it, or part of the ship that is a spinning drum. Okay, the occupants would stand, okay, kind of on the inside here, and it would spin this way. So their inertia wants them to do this, but the floor of the drum prevents it and pushes them back towards the center using reactive normal force. So it's not real gravity, because that would require a big planetary body pulling on you. It's artificial gravity. It feels like gravity, but it's not. Okay? It has the same effects as gravity, but it's not real gravity. Okay? But it would be better than having zero gravity all the way there. So if you've seen The Martian, I'll show you that on Monday. Not the whole movie, but the spinning drum part. Okay? You can see that they had that part of the ship that was a spinning drum, okay, where there was gravity. If they turned the spinning drum off, what happened to everything? It just floated away, right? Gravity, that artificial gravity, was gone. All right, I'm going to show you a couple of videos here of kind of some of the other challenges with being in zero gravity. Okay, these are all kind of Chris Hadfield's videos from when he was on the International Space Station. Okay, you'd be surprised how quickly you get used to not having gravity. I remember seeing an interview with him when he came back, and the guy who was interviewing him asked for his autograph. So he took the guy's pen, wrote on the paper, and then did this. Because he was so used to just being able to let go of a pen and have it just sit there, right? So he's like, oh, cool. And then click, and he's like, stupid gravity. Okay? Just because, you get used to not having to worry about that.